Hello everyone, welcome to another lesson of physics. Today we are going to start on FBDs, which are free body diagrams, and we'll also be talking about net force. Alright, so what is a free body diagram? So these are another type of vector diagram, and this is going to show all forces acting on an object, and these must be properly labeled. So we have an example right here of a ball just sitting on the ground or a table. So this is in static equilibrium because it's not moving around. Its velocity is equal to 0. And we got two forces acting on it, which keeps it in one spot. So pointing down, we have the force of gravity, or its weight. And then pointing up, we have this normal force. In a minute, we'll also talk about more forces that can act on this ball or other objects as well. All right, so every free body diagram, we are going to follow this method in order to draw them correctly. So first off, we're going to identify the object of interest, whether it's a ball, a person, a car. We want to identify what it is. Then we will put a convenient set of axes on the object. Then we'll draw and label all of the forces acting on the object. From there, for any force not along the axis, determine their components along the axis using trig functions. So if it's up at an angle. And then we are going to sum the forces in the x and y direction, the horizontal and vertical directions. And if these forces balance, then F net equals 0. There's no acceleration. The object is in equilibrium, either static or dynamic equilibrium. And if the forces do not balance, then the net force is not equal to 0. And then we can use our formula, F net equals ma, to solve for its acceleration. All right, so let's talk about all of the types of forces that we're going to see in this class. So there are a few different types of forces that we will encounter on a free body diagram. So the first set of forces is a contact force, which means that it needs to be directly in contact with this. If it's not in contact, then none of these forces will occur. So the first one is an applied force. Then we have the frictional force. Then we have the normal force, the tension force, and air resistance. So these are forces that occur when there's physical contact between objects. The applied force is some force applied on an object by a person. So for example, a person pushing a car is an example of an applied force. The friction force is a force that acts between two surfaces. This usually opposes motion, so acts in the opposite direction. An example would be dragging a cardboard box across dry pavement. The next force is the normal force, which is a force a surface exerts when pressed on, which can be an object sitting on a surface, a person pushing against a wall, anything in which an object is pushing against something. The next is the force of tension. This is a pulling only force that exists in any non-rigid material. So for example, a cable holding up a sign, a string holding something up, anything like that will result in a tension force. And lastly, we have air resistance. Air resistance is a special case of friction where an object experiences friction with air molecules. And this is going to act in the opposite direction as well. So an example, sticking your car out of a moving car window and having it be pulled backwards. Okay, so the next set of forces we'll be talking about are field forces. Some examples will be gravity, the electric force, and the magnetic force. And these are forces that act over some distance, so there's no contact required. They don't need to be in direct contact for these forces to be exerted. The first one, the gravitational force, is a force that exists between two objects with mass. Mass attracts mass. An example would be gravity on Earth. So we're probably all pretty familiar with this force by now. The next one is the electric force, and this is a force that exists between two charged objects. And maybe you learned this from chemistry, that if they have the same charge, they will repel. Opposite charges attract. An example is static cling. And the next one is going to be the magnetic force. And this is a force that exists between two magnetic objects. And just like the electric force, the same poles will repel and opposites will attract. So an example would be a magnet on a fridge. All right, so the next thing we want to talk about is net force. So if the net force is equal to 0, then we will know that our net acceleration will be 0, and it will be motionless or stay at a constant velocity, or some sort of state of equilibrium, either static or dynamic. And if the net force is not equal to 0, then it will be accelerating or decelerating. All right, so if we have some sort of object, like a mass right here, then we want to draw out the free body diagram. And if it's not moving to the left or right, then these are the forces acting on it. We got the gravitational force pointing down, the normal force pointing up. And if it's not moving up or down, then we can do our sum of forces, which we'll take a look at in a minute. So if we add up all the forces in the y direction, because up and down is the y direction, it's going to be the normal force minus the gravitational force is equal to 0. Or in other words, the gravitational force is equal to the normal force. Now, if we take a look at the x direction and said we had some sort of force being applied to the right, then we have this applied force. And if the ground is frictionless, then the only force in the x direction, when we add them all up, is just going to be the applied force. So since this is the only unbalanced force, it is also F net. So using our formula A equals F net over m, we can find what our acceleration would be if we knew how strong the force was and what the mass was equal to. Now let's talk about equilibrium. So a block with mass m is sitting on a frictionless table. Force is applied to the right, Fa. So the first thing we'll want to do is create a free body diagram. What would we have to do in order to put this block back in a state of equilibrium? So we have this frictionless floor, we have our mass, we have our forces in the y direction, the gravitational force down. Since in contact with the floor, we have a normal force pointing up. And then we have this applied force to the right. So the force that puts the system into equilibrium is called an equilibrant force. So there has to be some type of equilibrant force going to the left, which in this case could be someone pushing on the other side or something else to keep it in equilibrium. All right, so let's take a look at an example in which we have to solve for our equilibrant force. So we have this mass here, and let's assume it's on the ground, some sort of frictionless ground. So we always have the force of gravity pulling it down, and some normal force from the ground pushing it up. Since it's not floating up into the air or sinking into the ground, these two forces are balanced. Then we have a force of 10 newtons going to the right. So we need to find out what this equilibrant force is equal to. So if we want an equilibrium, then our equilibrant force will have to be equal and opposite to the other one, so it will have to be 10 newtons. Alright, so let's take a look at another example. So now we have a man pushes a 50 kilogram crate across a frictionless surface with a constant force of 100 newtons. So now we want to draw a free body diagram of the crate. So we have our 50 kilogram crate. So we got Fg going down, and upwards we have our normal force. And he is exerting a force to the right, our applied force, across a frictionless surface. So the first question is, what is the weight of the crate? So our weight is Fg, and as mentioned in previous lessons, Fg is equal to mg. So our mass is 50 kilograms, and we have our acceleration due to gravity, which is minus 9.81 meters per second squared, is equal to Fg. So when we throw these into a calculator, we will get 490.5 newtons. It's pointing down, so we'll call it negative. Next, we want to solve for our normal force. And as we said before, if this box is not sinking into the ground, it's not flying up into the air, then these forces in the y direction have to be balanced. So we can say that the normal force is equal and opposite to the gravitational force, which would then make it 490.5 newtons. So now we want to know what is the net force on the crate. So to find the net force, what we'll want to do is take a look at the sum of forces in the x and the y direction. So our sum of forces in the x direction, we're going to add up all of the forces in our x direction, which is only the applied force. And then we want to add up all of our forces in the y direction, which is going to be the normal force minus the gravitational force, which will end up being 0 newtons. Our net force is going to just be equal to our applied force, which we said before is equal to 100 newtons. And the mass of the block is 50 kilograms. So using our net force equation, acceleration equals net force over mass. We can plug in our net force, which we said is 100 newtons over 50 kilograms to get that our acceleration is equal to 2 meters per second squared. Now let's take a look at another example. So we have a horse that pulls a 500 kilogram sled with a constant force of 3,000 newtons. The force of friction between the sled and the ground is 500 newtons. So let's draw in our free body diagram as we always start off with. So we have the force of gravity going down. Then we have the normal force going up. We have some sort of applied force to the right. And then we have a smaller frictional force going to the left. So I'll draw it a little bit smaller so I keep that in mind. Now we want to know what is the weight of the sled. So we'll do this again, just like last time. Fg equals mg. We can plug in our mass of 500 kilograms and acceleration due to gravity, 9.81 meters per second squared, to get our weight equal to 4,905 newtons. So now we want to find what is the net force on the sled. So what we'll want to do is do our sum of forces in the x direction and the y direction and add up all of our forces. So in the x direction we have the applied force going to the right. So what we're going to do is we have to set up some sort of basis for which ones are positive, which ones are negative. So in this case we'll call to the right positive since that's the direction it's moving. Then we'll also call up positive as well. So since the frictional force is pointing to the left, we'll call it negative. And for the y direction, the normal force is up, so we'll call it positive. And the gravitational force is down, so we'll call it negative. Now, when we add everything up in the y direction, since it's not going up or down, we'll find that the sum of the forces in the y direction will be 0. And in the x direction, the sum of the forces, we can plug in our values. So there are 3,000 newtons being applied and a frictional force of 500 newtons resisting it, which then makes our sum of the forces in the x direction be 2,500 newtons. And since it's all in the x direction, our net force is going to be equal to everything in the x direction, which is 2,500 newtons. Next, let's solve for the sled's acceleration. So we can use our formula, acceleration equals F net over m, plug in our values, 2,500 newtons for our net force, and 500 kilograms for our mass, and get that our acceleration is equal to 5 meters per second squared. And that's how you would solve these problems with our free body diagrams and net forces. Alright, so that's going to be it for today. I hope you all have a great rest of your day.